All right, guys, so we've been going through power calculations, and in the last section, we derived three formulas that could potentially be useful when you're going through and doing the power calculations. There are a few extra formulas that I want to develop that are developed in the book. So here we're going to be exploring alternate forms for complex power. Now, we did find from the previous section, so we found that the complex power can actually be calculated if you know the RMS voltage and RMS current. And it can be calculated through this formula right here. So if I have the RMS current, I take the complex conjugate, multiply it by the RMS power, I can actually get the complex power, right? Now, one thing that we actually know is if we happen to have a load with a particular impedance, and there's a voltage across the load, and it draws a certain current, well, we know that Ohm's law, essentially, for impedances actually governs the behavior of that system as well. And we haven't taken that into account or advantage of that. So the circuit that we're picturing here is, suppose that we have some impedance here, and we place an RMS voltage across it, then we know that there's going to be an RMS current that flows through it like this. And the relationship between these three variables is kind of like Ohm's law. Well, it's the effective voltage is equal to the impedance times the RMS current like this, right? So this is the Ohm's law relationship. And notice that I'm actually putting this in parentheses. It's much more than Ohm's law, right? Now, if I call this equation 1 and equation 2, one of the things that I can do is I can actually use 2 in 1 by directly plugging in. So here, my complex power, well, it's still my effective voltage phasor. But now what I'm going to do is I'm actually going to plug in. Let's actually do it the other way around. I'm getting rid of the voltage and keeping the current. So here what I'm doing is I am taking this and I'm replacing it down. See, even professors have to be a little bit careful. So here I have my impedance times my effective current like this, times the complex conjugate of my effective current like that. Now this is one of the places where the complex number algebra actually comes into play. Remember that if you happen to have a complex number, so recall, for complex numbers, so if you have a complex number of the form z is equal to x plus jy, then the magnitude, which is the square root of x squared plus y squared like this, can actually be calculated much more easily if you take the complex number and you actually take its complex conjugate. This is important because notice that this very thing that we have here, we have right there, right? Which means that this complex power, well, it's the impedance times not the full phasor of the current, but it is the magnitude of the phasor current here squared, right? So you're only taking the magnitude, you're really disregarding the phase. We also know that this impedance right here can also be split into two parts. So this impedance has a resistive part plus J times a reactive part, right? So if I actually call this up here equation 3 and this 4, well, I can use 3 and 4, or 4 and 3 more like it. So here I can use 4 and 3, in which case we actually have that our complex power is actually equal to the magnitude of the effective current squared times the resistive part plus J times the reactive part. And if I just distribute these like that, I can even rewrite it as the magnitude of the effective current squared times resistance plus J, the magnitude of the effective current squared times the reactance like this. And this is the kicker. Notice that this, because of the appearance of J there and only there, this is automatically in the form of the real power plus J times the reactive power. That means that this term must equal the real power, while this term over here must equal the reactive power, and we get the following set of equivalences. The real power, if you take the effective current squared, is the magnitude of it multiplied by the resistance. That's one way in which you can actually calculate this effective power. Or the reactive power is the magnitude of the effective current squared, not times the resistance, but times the reactance. These equations are important enough to box as well, right? So this is an alternate way in which you can actually calculate the real or the active power or the reactive power as well. There's one last case that I really want to cover, and it really goes back to how we rewrote the generalization of Ohm's law, right? Notice that one of the things that we ended up doing here was we literally took V effective and we replaced it right there. One of the things that we could have done alternatively is we could have solved for the effective current and then replaced it there, right? You can even see with my T-shirt that there are multiple ways in which you can actually rearrange these terms and values and whatnot in order to give us something that's useful. So that's one of the things that I'm going to do is I'm going to solve for the effective current in 2 and then replace it in 1. So here, if I actually have equation 2, which is the effective voltage is equal to the impedance times the effective current, I can rewrite it as, well, the effective current is equal to the effective voltage divided by the impedance, right? And I can use this directly in 1. So here, remember that my complex power, which is V effective times I effective complex conjugate, well, I can again use this directly in them. But you do have to take care with the complex conjugate part. So here I have the complex power is the effective voltage times the effective voltage divided by the impedance times the complex conjugate. Now, when I take the complex conjugate of this term, I can actually distribute it essentially across the effective voltage and the impedance, in which case I get the effective voltage times the complex conjugate of the effective voltage, and be very, very wary, very, very careful. You'll have to take the complex conjugate of the impedance as well. Now, the top term is very nice because that's now just the magnitude of the RMS voltage, of the effective voltage, right? So this right here is the magnitude of the effective voltage divided by the complex conjugate of the impedance. Now, be very, 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 very wary. One of the things that we ended up doing up here when we were taking a look at the currents was we said, well, this must be of the form P plus JQ, right? Now, notice that you cannot split this apart very easily because the impedance here, right, is actually in the denominator. So this is r plus jx, right? And you actually have to do a lot more work in order to actually turn it into this particular form, right? So be very careful with your equivalences. In fact, one thing that I wasn't even careful of is when it comes to the complex conjugate, remember, uh, when I take the complex conjugate of this impedance, it is r minus j x, not r plus. So again, there's more things that you need to do in order to find equivalences. So here, the final note is S is equal to the magnitude of the effective power squared divided by the complex conjugate of the impedance, like this. And unfortunately, this is as far as you can go unless you make assumptions about what the nature of that impedance is. But this is important enough to box. That's one alternate way in which you can actually calculate the complex power. And you cannot go further.